What's it like reading the Feynman Lectures on physics? I'm sure you heard the name Richard Feynman plenty of times. Richard Feynman is one of the most legendary figures in the 20th century. He's well known for his contributions in physics through the Feynman diagrams. He helped with the atomic bomb during the Manhattan Project, and he was critical in the investigation for the Challenger disaster. He has an amazing book called Surely You're Joking, Mr. Feynman, and he has this amazing collection of books called the Feynman Lectures on Physics. So back when Feynman was a professor at Caltech, he had these lectures on physics, and he decided, and I think it was through a grant, to make these into books. And so far, this has sold thousands of copies. I will probably say millions, I'm not sure. But this is something that a lot of physicists and a lot of students and a lot of fans of Feynman like to purchase. Kind of like me. I think Feynman is an incredible, not just a physicist, but he's a great mathematician, and he was a very curious guy. And every time I will watch his videos or just read about him, I would just always feel so inspired just to continue learning. And one of the things that I saw in the Feynman Lectures of Physics, and to be honest, a lot of things just go over my head. I was just sitting, looking through a lot of the pages, and I stumbled upon an integral that just sort of looks familiar. This is something that we see plenty of times. We have the integral from 0 to pi of sine cubed theta, and I think it'll be nice to solve that. And just so you know, yes, I am a super amateur physicist. I don't quite understand a lot of the topics that are in that book, but I thought it would be nice to just solve this integral, one, because we see it plenty of times, especially in Calculus 1 and Calculus 2. So let's just go ahead and do it. So here we have the integral from 0 to pi of sine cubed theta d theta. And again, a lot of times people in Calculus 1 and definitely Calculus 2, you see this. You have sine cubed, so you have to do something about this using power reducing rules. Well, we can go ahead and rewrite sine cubed into sine squared times sine. Check this out. I'm going to go ahead and do integral from 0 to pi, and I'm going to do, this will be sine theta times sine squared theta. And what that's going to do is it's going to help us rewrite this. We know that sine squared has a nice identity with respect to cosine. Here's what I mean. We know that sine squared theta is equal to 1 minus cosine squared theta. This is the Pythagorean identity. So we can rewrite this entire integral, or this part of the integral, into, we have the integral from 0 to pi of sine theta, and then we have 1 minus cosine squared theta d theta. And that's going to help us out a lot, because now we can do a nice substitution. We can make our u value cosine, so u is going to equal to cosine theta. Then we're going to have du is going to be negative sine theta d theta. So we already have our du right here. This is our differential. We just need to make sure that we add a negative at the end. So what we're going to have so far is we're going to have the integral. We're going to have the negative sign on the outside, and we're going to have 1 minus u squared du. Now notice that I have not changed the parameters, or I didn't add them here, because originally our parameters were from 0 to pi, but now we have to make sure that we rewrite it because our integral is in terms of u. Well, here's what we have. When our lower bound was 0, we're going to have u is equal to cosine of 0. So when we have theta is equal to 0, u is equal to cosine of 0, which is just 1. Okay, that's our lower bound. And then when our upper bound is pi, we're going to have u is equal to cosine of pi, which is negative 1. So we have 1 to negative 1. 1 to negative 1. Well, here's what we can do now. We're going to flip this, and we're going to make this negative, and it's going to cancel out with that negative here. So now we have integral from negative 1 to 1 of 1 minus u squared du. And we can go ahead and start integrating this thing. And this is going to give us u minus u cubed over 3. Whoops, there we go, from negative 1 to 1. And now we can go ahead and start implementing the first fundamental theorem of calculus. Let's go ahead and plug in the 1 in here. That's going to give us 1 minus 1/3 minus, and now we're going to go ahead and plug in the negative 1, and that's going to be negative 1 minus, and then this is going to become a negative 1 because negative 1 cubed is negative 1. So this is going to turn into a positive 1/3. Okay, moving on. Let's go ahead and distribute this negative sign. This will be a positive 1. This will be a negative 1/3. So we have 1 minus 1/3 plus 1 minus 1/3. Combining this right here will give us a 2, and then this will give us a minus 2/3. And now we can get common denominators if we want to. Let me go ahead and put it here on the bottom. This will become 6 over 3 minus 2/3. And then guys, we are left with 4/3 right there. What does that mean in terms of the physics problem that Mr. Feynman was talking about? I don't know. Let's go ahead and check it out. Well, it looks like this was in the section of radiation damping, light scattering. Not sure what this will mean. I mean, it looks like the rate of radiation of energy. Again, this goes way over my head. I just thought that was interesting that this showed up in this particular lecture of physics. This is volume 1. So I'm curious, anyone that studied physics or can give a bit more understanding into how this relates to the radiation damping, please let me know in the comments. But otherwise, that's going to do it for today. Don't forget to like this video and subscribe, and I'll see you in the next one.